Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends to the 24th lecture on the course Maritime Structures under Fire, Blast and Explosion. We are continuing to discuss the sequel of Design for Blast sequel 4. Welcome to lecture 24 where we will continue to discuss further details about design of maritime structures under blast loads. So in the last lecture we discussed about the methods of analysis of structures under blast loads. When we talk about equivalent single degree freedom system, we already said that to establish equivalent single degree freedom system for analysis, because blast loads are dynamic in nature, therefore the analysis has got to be dynamic in nature. So we need to establish equivalent single degree freedom system. To establish, the basis should be governed by deflection, okay, not by strength or resistance. So the equivalency is on deflection. So, when we said that, we said there are two ways we can do this. One is a bilinear resistance deflection curve, other is trilinear curve. For our understanding, let me draw both these curves again to repeat what we discussed in the last lecture, but we will add more information to this now. We will add resistance versus deflection. Instead of saying it is stress strain curve. So, in bilinear, the actual curve looks like this. This is an actual curve. We idealize this as a bilinear curve. Let me say this part is so. The salient features, as we discussed in the last lecture, is that deflection at yield or elastic value. This is deflection which is the maximum value, and this is the resistance which is the maximum value. And the slope of this line will give me the elastic stiffness. This is bilinear. We copy the same bilinear curve here. So, these curves, the black one and the black one, are exactly same, okay, exactly same. I am just copied it. So, now I want to change this with an approximation of trilinear and take it here. So, now I can go this as maximum deflection. I can call this as the plastic deflection, and call this as the elastic deflection, and I call this as YE, small ye. This is capital E, okay, there is a difference. So, there are two slopes here. Let us say this is one slope, I call this as K1. This is another slope, I call this as K2, and this is a trilinear approximation. Okay, there are three lines here, trilinear approximation. Now, let us talk about this slightly more. Let us say in this Rm, which we can here also as Rm, is the peak resistance. Which is same in both the curves, bilinear, trilinear. Ke is called elastic stiffness of the equivalent system. We are talking about equivalent system here, friends. Okay, we are talking about equivalent system here. Ye is the elastic yield deflection. And Ym is the maximum deflection. Okay, generally the maximum deflection is taken from the bilinear curve, okay, this value usually. This is recorded for design purposes. Now, I can help you to suggest computing these values. Let us say Ye is given as Y small e plus Y plastic of 1 minus Rm by Re. Okay. So, where is Re? Please see this figure. I call this as my Re. So, I am incorporating the strength ratio back in working deflection. Okay? That is what I am trying to do here. And Ke, K equivalent is Rm by Y capital E. equation 1 and equation 2. Okay. So, now the approximations or idealizations made in the above discussions are as follows. There is an initial elastic region where the load increases linearly with deflection. That is an initial elastic region. Okay. So, I want you to refer to the trilinear part of this curve. Then it reaches an yield plateau. Where resistance stays nearly constant with an increase in deflection. Okay. That is what happens in bilinear curve. See here, resistance stays constant and deflection increases. Now, this is idealized into two pieces here. So, it does not happen suddenly. There is a reduction in stiffness, but resistance is not constant. So, it increases, okay, with deflection. Once it reached, then we reach Rm. So, this part is elaborated. It means before reaching Rm, it changes the initial stiffness and then changes here. Okay. So, that is what is incorporated here. So, we say and it reaches yield plateau and resistance stays constant, but then a strain hardening region happens. This is to be accounted for, is it not? This accounting is done with secondary stiffness. So, the secondary stiffness K2 is what you see here, accounting for the strain hardening part, this one. Okay. Having said this, the bilinear curve therefore is replaced by a trilinear curve, and the initial elastic slope is taken to be up to the yield point. Then the perfect yield plateau is now bifurcated to two parts. Okay. That is what we did. So, this idealization from bilinear to trilinear, okay, accounts for strain hardening, then includes ductility ratio effect, strength ratio effect, then energy dissipation effect. By modifying the stiffness from K1 to K2. So, there is a stiffness degradation, but this accounts for all these. Okay. That is what we did in the assumption. So, fundamentally friends, blast piston design fundamentally is different from conventional design, is fundamentally different from the conventional design, because this includes explosion induced loads. Now, one may ask me a question, What is specialty about these loads? Why they are so special? Because these loads import or impulse more force over a very short period of time. Okay, this behavior need to be captured. This behavior needs to be captured. So let us compare this with, let us say, I have a static force or I have a dynamic force like seismic force. I want to compare this with blast induced forces. I want to compare. Okay. I can now write blast induced forces are very short in duration. They vary significantly with distance. We have already seen the scale distance, stand-off distance, with geometry, because you know the peak overpressure on the front side, on the side of the building, top of the building are different, because the stand-off distance calculations are different. You could have seen the sequel lectures earlier. So, it varies with distance, varies with geometry, it also varies with material behavior. Now, this part of material nonlinearity related to explosion induced damage is not of course discussed in detail in this lecture or in this course. This is the material science expertise required to discuss this more in detail, but we touched upon the effect of this on steel and concrete. We will also do some design examples later, and Gaurav will explain how at least the fire induced explosion can reduce or can cause nonlinear response behavior to structural members like beams, columns, etc. Okay? So, the material behavior is not fully captured in the discussion so far, but I agree on that. We will work on that in some more examples in the coming lectures. But however, we have learned very clearly how the blast induced loads vary with distance and geometry, like how the explosion damage could vary if the scaled distance or the stand-off distance varies from the source to compare to the target. But these do not occur in static as well as seismic forces. So, blast induced loads offer a different design phenomena of structures. Why not maritime in general structures compared to other conventional designs? That is the take here. Okay. So, we can now write the blast induced forces are functions of, let us say they are functions of the charge of the mass, we can say the charged mass, which we say as T and T equivalence. We say the stand-off distance, the distance of the target from the source of blast, and most importantly friends, the nature of detonation, how the detonation happens. Okay? Even it does not only on the charge, but it also depends upon how do you detonate it. Okay? So, in the design phase, we account for all these changes in terms of estimating the acceptability of the system post blast. So, when you check acceptability, we check actually the deflection limits. Once I say deflection limits, then if it is concrete, we look for rotations. If it is steel, we look for ductility ratios. So, there are two different aspects of design friends. Okay? So, the idea in blast resistant design is not the strength aspect. Okay? It is more focused towards the safety, controlling the damage and preserving functionality. So, can I now say that blast resistant design is actually a performance indicator or performance based design? Because these are all performance indicators of a given building. Strength is of course an important aspect in the design, I am not denying that. But when you talk about blast resistant design, we focus more towards preserving the functionality of the structure, controlling the damage induced by the blast, and of course ensuring safety post blast of the structure. So, it is performance indicators, and we can say they are performance based design indicators. Okay. Therefore, friends, not all structures need to be designed for blast. That is a very important and critical statement. But when we talk about maritime structures, these structures are strategic in nature, they involve oil and gas exploration and production. Therefore, the catastrophic loss induced by blast and fire could be very severe order. Therefore, we need to check and do blast resistant design for maritime structures for sure. Okay? Therefore, blast resistant design, having understood it is a performance based design, or subset of performance based design, the indicators which we cover in the design procedures are importance of the facility, occupancy type, acceptable damage levels like low, medium and high, and then we set the design objective based on this. Okay? So, the performance indicators play a role in even governing the design objective of the system. So, the ultimate goal is the structure should not have any structural damage, but the structure can have non-structural damage. It is permitted. Okay? That is what the over section is. To do this, therefore, the design should focus on 1, the member sizing, the member layout, the geometry we say. Okay? Then of course, we agree that ductility is a very important aspect, and we should also have some energy absorption mechanisms, friends. Therefore, friends, control of system, control of structural response, be it active, be it passive, be it hybrid, becomes very necessary for blast resistant designs. Because the excessive response induced on the system should be absorbed, should be compromised and compensated by external control devices. You can also look at detail. There is a book authored by me on earthquake engineering and structural control, okay, which we did for CRC Press. Please have a copy of this book in your library, and this will tell you lot of methods of structural response controls which can be deployed on various structural systems, including examples on maritime structures. Now, let us try to find out what would be my design objectives. The design objectives under blast loads, that is for blast resistant design. What should be my objectives? One, the foremost objective, maintain structural integrity after the blast. Total collapse is not accepted. 2, we must prevent progressive collapse. The cascading effect of the design should be avoided. Thirdly, allow controlled deformation and energy dissipation. So, we must deploy the control mechanisms to induce the dissipation energy concept to avoid brittle or sudden failures. Okay? These objectives need to be fit into the dynamic response behavior, understanding of the structural system, and enough ductility and detailing. Ductility should be the governing factor if you talk about steel design. Detailing, that is structural detailing, reinforced detailing, then rotation at joints should be important when we talk about reinforced concrete structures. So, should become an implemental ideas or design objectives in blast resistant design of structures. Having understood this, now let us go one by one and try to understand how do we take element wise this category of understanding. First, let us talk about slabs and walls. Slabs and walls primarily resist out of plane bending. Okay? Slabs and walls primarily resist out of plane stresses. They also have in plane stresses, but that is very rare application except in case of systems or workshop floors where friction load is much effective. Okay, because generally slabs and walls have a diaphragm action which exhibits out of plane stresses under the given lateral loads. Therefore, the response offered by them is essentially flexural, and the failure posed by them is essentially due to plastic hinge formation. If the rotation exceeds the plastic hinge capacity, okay, then failure initiates. So, that is how the slabs and walls actually generally fail. Now, if you look this aspect in blast resistant design, we should say that slabs should have two-way reinforcement. Two-way reinforcement does not mean the slab is a square slab. I am saying two-way both in the top and bottom of the slab. It means if the slab is this way, I must have reinforcements on the top as well as on the bottom This is a slab whose thickness approximately will be 150 to 200 mm if it is a reinforced concrete slab. Okay, it should be both way reinforced, right, two-way reinforced, because this will form a mesh interaction. Therefore, this can form a dense mesh which can withstand the blast loads. Okay. You must have also covered this kind of idea in blast resistant glass panels. You would see that the fibers are provided on both sides of thickness of the glass, and the glass is glued to these fibers on both composite layers before the glass is extruded for manufacturing these pans or panels which are blast in resistant panels. So, that should be the idea of doing the reinforcement on both sides, and reinforcement should be anchored should be provided with proper bond development length. Okay. They should be able to transfer the load through the bond action properly, and they should be avoided with pull out forces. They should not get pulled out from the support. Okay. Let us talk about the other element, which is beams and girders. Beams, let us say plate girders, okay, gantry girders. Now, these are common elements in maritime structures deck system. Talk about beams and girders. Now, friends, these structural members are subjected to counterflexural bending. What do you mean by this? Let us say I have a beam, maybe simply supported. Under blast loads, they will have alternate bending, this way and this way. Okay? So, counterflexural bending from blast waves caused by blast waves. Can you tell me how this is possible? Look at the blast wave. The blast wave from atmospheric travels reaches its peak, okay, then falls and creates a suction drag for a long period actually, and this suction will induce reversal of bending. Okay, this is the problem. So, caused by blast waves will have counterflexural bending. Therefore, the members will have or will experience plastic rotations at support and also the midspan. That is very important. Therefore, shear reinforcement in case of RCC beams or web stiffening in case of steel girders are essential to counteract this effect. Okay. Let us talk about the third element, the compression member. This is the column element or compression members. I mean direct compression, not bending compression, direct compression. Bending compression comes from beams. Okay. Now, column members are more vulnerable to blast because column members have a different problem of losing its strength under buckling behavior. Okay. So, it has got a combination of axial load and bending. This PM interaction is a big trouble the column face, is a big complexity. So, the load carrying capacity, both moment and force, gets reduced under this joint interaction. Therefore, the vulnerability is columns may trigger progressive collapse. So, which is not permitted in case of blast resistant designs. Therefore, to avoid this, in case of reinforced concrete columns, one should go for providing lateral ties at closer intervals. In case of steel columns, people should go for battens or lacings to strengthen the column from PM interaction and stability failure. Okay. Now, let us take up another point which is also important as an element, which is connections. Joints, connections. Connections are very critical generally because they undergo rotations which, if exceeds the plastic capacity, then there is a failure. Okay. Certain times it induces brittle failure. If the ductile detailing, is improper in case of reinforced concrete sections. So, generally connections lead to, or connections failure lead to, global collapse, though it starts from a local collapse. Though it starts from a local failure, it leads to a global collapse. The whole structure can have a catastrophic failure. Okay. So, how to avoid them? How to control them? Controlling is very simple. We can have reinforcement anchorages, proper anchorage of reinforcement. These are all about RCC. For steel, we should have mechanical connectors, or you can also have a strong welding practices. Okay. The other element is also subjected to this problem is the roof systems and ceilings. Yeah. In case of lightweight roofing, okay, or in terms of claddings, which are generally common in industrial structures, then the elements can detach from the primary system under uplift pressures, and under blast, okay, they travel as projectiles and they will hit people as well as structures. That is the danger, because they can easily get detached from the primary system and they start travelling with the sound velocity. So, that is the important problem we have here. So, friends, we will come to the summary of this lecture. In this lecture, when we spoke about blast resistant design, we understood why this design is different from the static loads or even dynamic loads like earthquake loads, why they are different. We have also understood and reiterated the bilinear and the trilinear curve. Then we realize what are the different structural elements, how do they respond under blast loads and how they should be designed to withstand them. So, we further continue this discussion as a sequel of the next lecture, and we learn more about the summary details and then the control checklist for blast resistant design as applicable to maritime structures. Thank you very much. Namaste.